Okay, welcome back. This will now be the third lecture, so the midway point of the lectures on the application of tree automata theory, and this will conclude the section on parsing. So I said advanced topics because I kind of wanted to keep it open till the last moment of what I actually will do. But you'll see now, of course. So we are here. So the first part today will be the more strenuous part, the more theoretical part, as usual. So we'll talk about an advanced topic in parsing, something that I nevertheless hope is interesting to you, and I'll tell you why it might be interesting to you. And then the second half today we'll spend on the introduction to machine translation, which is a bit lighter, and I hope you have some fun there. There'll be some nice Russian examples there again. Okay, so let's start. As yesterday, please ask questions if you have any, right? So don't be shy. Let's start. What did we do so far? I gave you an introduction on the foundations of tree automata, right? So you should, by now, I wouldn't say be comfortable with tree automata, but at least you should have some idea what they do. And we'll, of course, see all those models that we had yesterday again and again and again. And I also tried to show you how you can actually use those devices in natural language processing, in the parsing application here. So I showed you that all of the state-of-the-art parsers, at least for English, are tree automata. And if you have a clever algorithm for tree automata, then you should try to make it work for a parser as well, which might require next to no adjustments because it is syntactically a tree automaton, or it might be next to impossible because those devices, for example, are never deterministic. If your algorithm only works for deterministic devices, you're kind of screwed. And today I want to do it's kind of like the other way around. So here you could get your devices and you solve a problem for that device. And here now we'll do it the other way around. We'll try to import a bit of tree automata theory into natural language processing. So we'll try to solve a problem of theirs, a theoretical problem of theirs, using the theory that has been developed for tree automata. Okay, and the problem that I chose, there are many actually to choose from. I chose lexicalized grammars simply because, well, it's a nice area that is relatively easy to explain, and we already had the mention of tree adjoining grammars, so they'll reappear today actually. Okay, let's start. So this is just a Merriam-Webster, it's a dictionary entry for the word sleep, right? So what can you find there? You can find it's part of speech. So in this case, it's a bit more specific. So normally part of speech would only be verb, but here you find some more information that it can be an intransitive verb, and then here are the meanings if it is an intransitive verb, and that's the typical meaning, right? So these here are ordered by frequency. And then it can also be a transitive verb. Most people might not realize that sleep can be used as a transitive verb. If you ask a linguist, he'll immediately say it's an intransitive verb. It doesn't take any objects, right? But actually there are ways that you can express things with sleep in a transitive way, like slept, the sleep of the dead. That's a construction, and we'll get to those in a minute, which means nothing else than it's a glorified way of saying that you sleep in something. Or sleep away the hours, that's also kind of like a fixed phrase for spending time by sleeping. Or the boat sleeps 6, yeah, provide accommodation for. So these are just constructions which are rare, but they're using the word sleep as well as a verb. Okay, and there are some others which might not be so. Well, here you actually see a particular construction which is triggered by a preposition, but that's not a transitive use, right? That's a prepositional phrase that is added. It's not an object. Okay, so here are some fragments that you'll see for sleep, and these fragments, they're very important to a linguist. So the linguist wants to know, okay, this is a very common fragment for sleep, and it says this is an intransitive use of sleep, right? It's a verb phrase by itself. It's only the verb, doesn't have any objects. Here's another intransitive use of sleep with a prepositional phrase. So you sleep in a bed, but that just determines the location. It's not an object. Or you sleep for 5 hours. That just specifies how long. It's not an object to the verb. Here, for example, you see this particular construction, sleep with, which has a slightly distorted meaning from the usual sleeping. And here you see a transitive use. So this is how a transitive use would look like. Right? Here's the verb, and the verbal complex here is made up not just of the verb, but it takes a noun phrase as an object. And you could also imagine, actually that's not possible for sleep, but there are also verbs which are bi or ditransitive. They take two objects, like give, right? You have to give something to someone. So there are two necessary components. Okay. So in such constructions are a major research area, not for computational, but for traditional linguists, right? For them, reading the newspaper is work, right? They read the newspaper, they try to find out, oh, here's somebody used a certain word, a verb, a noun, in a creative, in a imaginative way that is somehow different from the standard usage. They'll underline those or mark them somehow, and they'll later go to their files, they copy it down, and in this way they try to catch how language is evolving over time, right? I'm pretty sure that sleep with originally had no different annotation than just to be sleep next to somebody, right? This additional meaning developed over time somehow as a means to express something else. Okay. So what is a lexicalized grammar? This is again a meta definition, just because I want to avoid defining it for every type of grammar. So assume that you have a grammar which has a production set P, and such a grammar will be called lexicalized if each production in it contains at least one lexical item. So remember, lexical items were the words of the language, like sleep. Okay, that's just a definition. You can plug your favorite grammar formalism into it, right? So for example, you can immediately realize that non-deterministic finite automata, if they don't have epsilon transitions, then they are lexicalized, right? Because you always take one symbol and you transition to a new state. Each production looks like this. Or a context-free grammar, this need not be lexicalized, right? Because you allow productions like S goes to NPVP. There is no lexical material in this one. So, but if you have a context-free grammar in what is called Greibach normal form, then this is a lexicalized one. And if you don't remember what Greibach normal form was, that was, you have a non-terminal that is developing into a terminal followed by a sequence of non-terminals. This is Greibach normal form. Okay. Why would you look at lexicalized grammars? Well, first of all, they're really ideal for parsing, right? If each rule contains a lexical item and you get a sentence, then you can immediately say which rules are certainly not useful. Because all the rules which have other lexical items that you don't have in your sentence, you can just discard. That makes your production set so much smaller, which is really, really useful if you want to parse. Second, since each production adds at least one lexical item, there's a very hard bound on how many productions you can actually use, right? You can only use as many as you have lexical items in your sentence. And what is actually the most important thing, because this parsing, well, you can also live without those. So parsing can also be done in the usual n to the cubed way, right? For context-free grammars, say. But this is actually the most important thing. So if you have a parser and this is additionally lexicalized, then you can read off linguistic constructions, right? You can look at the productions that contain the verb sleep, and you can see what are constructions that are possible, right? Is it most of the time? You can look at the weights of the productions as well. Is it most of the time transitive, or is it not transitive? Does it prefer certain prepositions over others? This is the kind of stuff you want to take out. And there are some theoretical advantages to this as well, which I'll not go too much into here. There are, of course, some disadvantages as well. So they have only finite ambiguity, such grammars, right? Because you can only use finitely many productions, it means that each sentence can have only finitely many parsers. It's kind of clear. Now, if you were a linguist, there would be a lot of arms going up, saying, well, why is this a disadvantage, right? This is totally natural, that the sentence should have only finitely many ways to explain it. Why should it have infinitely many ways to explain it? Well, in general, context-free grammars have this concept that they can have infinite ambiguity. But indeed, so I'll put it down as a theoretical disadvantage. If I were talking to a group of linguists, I wouldn't do that, okay? Okay, let's go into lexicalization. So this is now the process of making a grammar lexicalized. Of course, keeping the semantics. So here's the definition. So two classes of string grammars. Let's start with string grammars first. So they produce strings, like context-free grammars, like regular finite automata or deterministic or non-deterministic, doesn't matter. And you can say that a grammar G prime weakly lexicalizes another grammar class, so sorry, a grammar class G prime calligraphic weakly lexicalizes grammar class G if for every grammar that you can choose from the class that is lexicalized, you can choose an equivalent lexicalized version of the other class, right? So they have to produce the same strings, but these here, the guys here, have to do it in a lexicalized way. What can you say immediately? Well, that's a very famous proof, so due to Greibach, as you would expect probably, that context-free grammars can weakly lexicalize themselves. Because for every context-free grammar, you can construct an equivalent context-free grammar that is lexicalized in Greibach normal form, if you prefer the theoretical saying. Okay, so that's okay. And this was actually good evidence for the linguists. But there are some problems with this definition. And here are the problems. So weak lexicalization only covers the generated string language. If you know the construction, Greibach normal form construction, you know that the grammar that you'll end up with will look totally different from the grammar that you started with. Which means, however, that your parsers will suddenly look very, very different. If you remember how the derivation trees for a Greibach normal form grammar look like, and the ones for your original context-free grammar look like, there is next to no relation between them. It's a very annoying thing. And of course, that is, in nowadays world, not acceptable anymore, right? So weak lexicalization will destroy all the linguistic knowledge that you have in your tree bank. Because suddenly you have non-terminals which have no meaning anymore. There's no more NPs and VPs, but they're suddenly unnamed entities, right? There's just X and Y and Z. They have been artificially introduced during the lexicalization process. But that's not meaningful to a linguist anymore. How is he supposed to read off the constructions now? He will say sleep, but then it will have, on top of it, it will have Z and Y. But that's not meaningful to the linguist anymore. So these lexicalized context-free grammars, the weak ones, are not very useful, at least for constructions. Reading off constructions, not useful. For parsing, they are useful, of course. Now, the solution, of course, will be to go to the tree level, right? So we want to keep the trees intact so that the parsers stay the same. So first, there's one minor definition. The yield, that's simply a mapping from trees to strings of leaves, and the yield of a symbol, Q, a leaf symbol, is simply that Q. And if you have a bunch of trees joined under a root symbol, then you just read off the yield of the first subtree up to the yield of the last subtree, and you concatenate all this. The effect of this will be very simple. It will just be reading off the leaves in sequence left to right. So that's just the yield. The yield of this tree we must bear in mind the community as a whole. So for this constituency trees, this will always give you the sentence that you wanted to parse. This is not true for dependency trees like this one, right? You remember this from yesterday. There was a Russian sentence that is represented here. I can't read it, as you know. So, but if you take the yield, you'll get only this. Because some Russian words are represented in here, right? So these are also Russian words, but they're not part of the leaves, so they won't occur in the leaves, right? So you only read off this, 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 the comma, and the 20. That's just the yield. So you would have to define the yield in a different way for such trees. But as I said, we'll mostly deal with constituency here. And then I already told you that there is a theoretical disadvantage, and we have to take care of that. So now we'll define the concept corresponding to that theoretical disadvantage, namely a tree grammar G is finitely ambiguous if for every string there are only finitely many trees accepted by the grammar that have the yield W W. So this is the restriction, the set of parses of W, which is the set of trees accepted by the mechanism that has this particular yield, is always finite. Okay? If it's infinite, you cannot hope to lexicalize it. There's simply no hope, right? Because if you have a lexicalized grammar, you always have a finite set of parses. So this is a restriction that you'll need to make in the very beginning. But again, if you're a linguist, you're very happy with that definition. You would say every grammar should have this property. If your grammar doesn't have this property, it's not a good grammar. Okay, now we go to the main definition for today. And that is the definition of strong lexicalization. And it's actually not different at all. You just look at tree grammars now. So you have two classes of tree grammars, and you say that the class G prime strongly lexicalizes the class calligraphic G if for every finitely ambiguous, so you make this restriction, grammar of the class that is lexicalized, there exists an equivalent one, so same semantics, lexicalized version in this primed class. Okay, so it's the same process, right? If you want to lexicalize, you have to find an element in this class which is a lexicalized version computing the same semantics as the one that you started off with. And to make this work, the original one has to be finitely ambiguous. Otherwise, you can't fulfill this. Okay. Now here's the first question. As usual, you know, there's some audience participation part. So here it is. So local tree grammars. Remember, these were just context tree grammars working in tree mode, so to say. Can they strongly lexicalize themselves? So remember, context-free grammars were able to weakly lexicalize themselves, and the main method there was the Greibach normal form. Now you go to the tree level. Can they also be made such that each production contains a lexical item without changing the derivation trees? Any thoughts? Who wants to hazard a guess? Okay, it's of course a bit hard, but I already tried to tell you that you basically have no means to change the grammar without changing the derivation trees, right? If you introduce a new non-terminal, you're going to change the derivation trees. So although I cited somebody, that result is actually relatively easy to obtain, this cannot be done. So there are easy counterexamples. Now you might say, okay, it cannot be done with the local ones. Maybe it can be done with the tree substitution grammars. Any thoughts on that?
No, it cannot.
It cannot? Ah, it's a good idea. Can also not be done with the so this is actually what he proved, right? This is a bit more difficult than the local tree grammars. So it cannot be done with the tree substitution grammars either. Just having big fragments doesn't help you at all. What about RTGs, so regular tree grammars? So now you have states. Now you can actually make things disappear. Does it help? So you're not in favor? This is based on the amount of space that is not visible, or? You're of course right. Can also not be done by regular tree grammars. So it's not due to the fact that you don't have state information. The mechanism is simply too weak. So this is one of the things where regular tree grammars are not sufficiently strong. And this is actually part of the story that I tried to tell yesterday, at least in part, And this is one of the motivating things for linguists to go to stronger devices. And the devices that they looked at were tree adjoining grammars. And they were already mentioned yesterday. And for those who don't know them, they'll have their chance now. So you get to know tree adjoining grammars. What are those? They're called a mildly context-sensitive formalism. That just means they are more expressive than the context-free grammars, in some sense. The productions express local dependencies. That's typical for grammars, but they can actually realize global dependencies. So you can actually realize quite complicated dependencies. But this is more linguist speak, right? It doesn't say much to a theoretical person. However, these have been used extensively. So there's been a long-running project called the XTAG project, which ran for, I think, more than 10 years. And they came up with a tree adjoining grammar for English. This has been a huge project with a lot of collaborators. And this also exists in more specialized terms. Since we're doing with lexicalization here, there's also, for example, a lexicalized tree adjoining grammar for German. And this has been done in another 5-year project worth about 1.5 million and finished in 2010. Okay, so these are actually used. So tree adjoining grammars are used. Not my favorite grammar formalism, but they are actually used. Okay, so what are they? So actually here you see they've been invented very early on because the need for linguists was clear. Once you couldn't do it with tree substitution grammars or anything similar, you had to come up with a more expressive formalism that is able to lexicalize at least the context-free grammars, right? Because that was like the staple of a linguist, right? You had a context-free grammar and you want to lexicalize it to see which productions are possible. So this is the main definition. It's again a set of, well, kind of context-free grammar non-terminals. So these are these weak non-terminals that will occur in the trees, but they have to be rewritten. They're not allowed to occur at the leaves. Then you have some internal and terminal nodes. There's a set of start non-terminals and a set of rules or productions. And this is, of course, finite, the set of productions. And you have two types of productions. I'm not spelling this out in full detail here. You have substitution productions, which are exactly the productions of a tree substitution grammar. Exactly the same. It's just a large tree fragment, which might have non-terminals at the leaves, which will then have to be replaced. And it has a second type of production, which are called Injunction Productions. And these have a very special form. Namely, there's a non-terminal at the root, as always, like in a context-free grammar production. This is what is going to be rewritten. And then there's a tree fragment. There can be non-terminals at the leaves that have to be rewritten. And there can also be one special symbol, which has to be the same as the one at the root, marked with a star somewhere at the leaves. So this is the special shape. Yeah, you'll see another way to express this in a, at least for me, much cleaner formalism, and this will be introduced in full detail. Just for the moment, try to appreciate this maybe with the following example. So you start with an initial non-terminal like this S, and I'll box it so that you see that there might be something going on with this one. So then you can use a substitution production like this one. I will rewrite the S into NPVP, and we've seen this, of course, a couple of times already. And here you might have to actually, in the formal definition, you have to keep those two separate. So they are marked somehow. And this is just substitution. And now next, I think I'll do something special. Namely, I use this one, which is this weird sort of non-terminal, right? This is the context-free grammar non-terminal. But here it suddenly can also be used as a trigger for an adjunction. So now I can replace things inside the tree. Not at the leaves anymore, but inside the tree. So what will happen? Here's an injunction production. And what I will do, this injunction production can fire whenever I see an N somewhere in the tree, and it will fold into this part. So here's the N. And I'm going to fold, this production in here. And what is below will be attached to the n star. Right? So I'm just going to glue it into this part of the tree. And this might, of course, trigger new non-terminals which can be rewritten. Okay, so this is how a tree adjoining grammar works. Of course, there's a derivation mechanism which I didn't define now, but you start from an initial non-terminal and you try to get to a tree which has no active sites anymore. Again, I didn't define what the active sites are, but you'll see a stronger mechanism that is fully formalized. Okay, what can tree adjoining grammars do? Well, they can do quite interesting things. So if you have those productions here, so by the way, this is a substitution production, this is an adjunction, adjunction, adjunction. The easy trick is always to look for the star, right? So if you see a star, it's an adjunction production. So here's, assume that you're in this situation. You could now use this production, but that wouldn't be very useful. So in this case, I used this production, and I unfolded this S here, and you're going to substitute this in. The C, which was below the S, is going to be below this starred S, and the star disappears. So this is what you get. Then you can expand this S, maybe with the B production. You're going to end up there. And you can do this again, and again, and again. And what you'll see is you're going to, at the same time, grow this part and this part. Right? Because you have this recursion now which is in the middle of the tree. And this allows you to, for example, construct a language that is WCW, because you can imagine that this here will always be the same as this here. Which is not context-free, right? Okay, good. This is no longer context-free, so this mechanism can generate non-context-free string languages. So it's more powerful than the regular tree grammars. They can only generate context-free string languages. Okay, then there was a famous result in the 90s. It's actually a PhD thesis, which says that tree adjoining grammars can strongly lexicalize local tree grammars, so in some sense context-free grammars, and themselves. Okay, unfortunately, there's some space, as you can probably see. It's not true. Turns out, well, a bunch of years later, almost 25 years later, turns out, well, the first part's true. It can lexicalize local tree grammars. Second part's not true. They cannot lexicalize themselves. So this has been proven by Kuhlmann and Sattau in 2012. So it's true that they can do what you really want them to do. So they can lexicalize context-free grammars. So you can read off the productions if you have a parser that's based on a context-free grammar or a regular tree grammar. You can read off the productions in this tag that you get when you lexicalize. But the main motivation why tags were so appealing was that they can lexicalize themselves. Yeah? You could iterate the production if you wanted, this lexicalization if you wanted to. So even if I give you a tag, you could turn it into a lexicalized one, according to this result here, but which is not true, unfortunately. So this has, of course, been reiterated a couple of times. So this lexicalized tag project for German has a final result, which is a book, Parsing Beyond Context-Free Grammars. You'll find the result in there. It was just 2 years too early, right? So then, of course, the main reference for tree adjoining grammars, which is in the Handbook of Formal Languages, is a whole chapter on tree adjoining grammars. Also, of course, reports on this result here, the wrong one, of course. And there's another chapter in another rather famous handbook, which will also tell you that they can lexicalize themselves, and they even give the wrong construction, so to say. But unfortunately, it's not true. And I'm not going to show you why it's not true, but I'll rather show you what you can do about it. And this is the mechanism which is, again, this is a mechanism that has been studied in the theoretical computer science literature. So this has had nothing to do with linguistics in the beginning. So these are context-free tree grammars, right? So once you have regular tree grammars, you have somehow an urge to define context-free tree grammars as well, right? Because it always starts with regular, then it goes to context-free, then it goes to context-sensitive. Well, Actually, for tree grammars, we stop there. It gets kind of difficult already at context free. So, of course, there is a concept that is a context-free tree grammar, and this is how it looks like. You see it's been defined around the same time as the original tree grammars, regular tree grammars, and it has the same components, only that you're allowed a bit more flexibility. So here you have a non-terminal, real non-terminal, so states, internal and leave symbols. This is now collapsed into one set. Start, non-terminals as usual, and productions. And the productions have a more, well, they have more allowed shapes, so to say. The production set looks like this. So each production is a non-terminal followed by a bunch of x's, variables, and it goes to a right-hand side. And the right-hand side is a tree in which the non-terminals may occur, the internal symbols may occur, and the variables x1 to xk may occur. Of course, the variables can only occur at the leaves. And there's a restriction, this is why there's a C here, for the device that we'll look at. All the variables have to occur exactly once. Okay, you can look at the device without this restriction, then you get nonlinear devices or deleting grammars, and we'll not do this. So in general, you can imagine a T here, and then it's the definition that you all know, right? Just trees. And that's the general definition that was given by Rounds. We'll only use the simple variant, let's put it like this, right? Where all the variables will always occur in the right-hand side. So if you're supposed to use the variables x1 to xk, because they occur in the left-hand side, they also have to occur in the right-hand side. So here's a quick example. So this is just a bookkeeping material, so to say, right? So it's just saying what kind of symbols are allowed. And here are the productions. So S can develop into A, alpha, alpha. Or A, beta, beta. Or sigma, alpha, beta. And A can have two variables, and then it develops in this way, or it can also develop in this way. Let's see this in action. So this is just a graphical representation of the whole thing, right? So that you don't have to read this textual stuff all the time. So you can represent this graphically, and I'll try to keep the variables colored so that you can easily distinguish between them. Let's see how this, so I'll not do this textual representation in the future, it's just annoying. So let's see how this actually works. So here are the productions. If you start with an S, you can of course use this production here, and you'll have an A and two alphas. Now you can use one of these A productions. Here's one, here's the other. Let's use the first one, right? Otherwise the fun's over in a minute. So let's use the first one. So this regenerates an A at the root, then a sigma x1, this was the alpha here, right? Marked in blue. An S, sigma, another alpha because that was the second parameter, and an S again. And now you can continue this process. So you can develop the S here again into an A beta beta. You can develop the other S into this one here, sigma alpha beta. Here you go. And then here you still have to develop these two alphas, but I'll use this rule now, which just replaces the alpha by a sigma. Oops. So it'll just be replaced by sigmas. Okay. So far, so unclear? Okay. Generated language, I think I have this definition 5 or 6 times in all the slides. So of course you start with an initial non-terminal, you try to derive a tree which has no non-terminals anymore, and that's the language. All those trees that you can derive, that's the language. Okay, and fortunately, even the guys who actually introduced tree adjoining grammars later realized, oh, maybe we should have actually taken this context tree grammar mechanism because it's so much cleaner. You don't have to say what an adjunction site is and whether it's an obligatory adjunction site or whether it's an enabled adjunction site. I skipped all of this, right? I just said at some point certain internal nodes might become active. There's a whole bunch of formalism which tells you when such sites may become active and when they have to be closed and cannot be used anymore. It's all nonsense, can all be triggered by the states. The state behavior of a context-free tree grammar will give you all these facilities. So this was originally remarked by the authors of TAG. Of course, they were strong supporters of TAG, so they couldn't make this formal. They just noted it in passing. And it was later formally proved by Manish in '97 that for every, well, this is a strong variant, so it includes the normal TAG. There's an equivalent context-free tree grammar of this particular shape. And if you look at such an Injunction Production n generating an adjective to the left, then you'll have a context-free tree grammar production where this n has one parameter, and it can put an adjunction to the left of it and then reproduce what was previously there. So it's a very natural translation. Very easy. And now let's look at lexicalization of TAG, right? This failed for TAG. And this was proven by Kuhlmann and Sutter that you can't do it for TAG. So you will need some technicalities here. But this is a very easy one. So such a context-free tree grammar is start separated if you have a single initial non-terminal. I guess you can imagine how to do this, right? It's done in the same way as you would do it for, say, regular tree grammars as well, or regular grammars even for strings, or for context-free grammars. And the start non-terminal, the one that you have, doesn't even occur in the right-hand sides. So you just eliminate recursion for the start non-terminal. Well, you can just do this. Of course, there's not a big surprise there. I wouldn't even know whom to cite for this. Okay, I just told you how to do it. Now this has already been a bit more complicated one. So a context-free tree grammar is growing if all non-initial productions, so these are the productions that don't have the start non-terminal on the left-hand side, contain at least 3 non-variables. Okay, so this production here, A x1 to x2, goes to this one here. That is growing. That would be okay for a growing grammar, because you have 2 variables, but 1, 2, 3, 4, 5 additional symbols. No problem. This one is a problem. This would not be okay in a growing grammar, because this only has 1 non-variable symbol. And fortunately, some other people helped us there. So they did it in a completely different context, right? They had nothing to do with linguistics or anything like this. So Starmer and Otto in 2007 proved that for every context-free tree grammar, there's an equivalent one that is growing. Okay, so you can probably imagine how this works. You have to glue rules together until you have enough symbols, so to say. Okay, so you can turn every context-free tree grammar into a growing one. The start separation is so easy, I'll just skip it from the diagram, right? You can always do this. Okay, now let's look at this example. So this is the grammar we've seen before. Now how would you actually get to this growing mechanism? Well, somehow this grammar, this rule here, the last production, this A x1 to x2 goes to sigma x, x1, x2. That is, of course, the problem. And you substitute this one into all the A productions, so to say. So here, you could trigger this production at this point. So you're going to, you will have it's just a shorthand here, you can have A or sigma here. So you get a production where A can generate this A as before, or it can generate the variant where you have a sigma here, because then you would have used this production immediately afterwards. And you do the same here, and you're done. In this case, in general, you have to do a bit more. But this is just the intuition how to actually remove such productions that have too few non-variables. Okay. Now, this will be even slightly more technical, but it will actually make the final proof a lot easier. So the context-free tree grammar is monad, or a production in it will be monadic if the right-hand side contains at most 1 non-terminal. Right? So you're only allowed to have 1 non-terminal in the right-hand side. Then it's a monadic production. And similarly, it's called a terminal production if there's nothing left to do, right? If there are no non-terminals in it anymore. Okay? And now you come to the main definition that you'll need. A production is lexicalized if it contains at least 1 lexical item. That's really not surprising, right? That was the definition already that I gave, the meta definition. But we'll need a funny one, which is called doubly lexicalized. And it just, you have to have 2 lexical items. Okay, that's just a definition. Okay, so sometimes you need 2. And you'll see in a moment where you need 2. So lexicalized, 1 lexical item, doubly lexicalized, you need 2 lexical items. Okay, and then in 2012, we're able to prove that for every context-free tree grammar with finite ambiguity, otherwise you're shot, right? You cannot lexicalize. There exists an equivalent context-free tree grammar such that all the non-initial, so the initial ones are really boring, monadic productions are lexicalized. So if you have a production that can only produce 1 new non-terminal, then it's already lexicalized. It has a lexical item. And if it's a terminal production, then it even has 2, right? Then it even has 2 lexical items. And this is not yet the main construction, so I won't show you how to actually do this. You're again going to remove something like epsilon productions, and then you try to compute some kind of closure, but it's all efficient and effective. So now you're at the stage where you turn the growing one into a fully normalized one, which is the one that we call this here fully normalized. Because now we're not doing any normalization anymore, and we don't have much to do anymore anyway, right? So these are already lexicalized. The monadic productions are already lexicalized. The terminal productions, they're even doubly lexicalized. Now there are those productions which have at least 2 non-terminals. These are left. And I have no restriction for them so far. So this I have to do something about. But fortunately this also worked. Every context-free tree grammar with finite ambiguity can be strongly lexicalized, and of course this is only the final step in this chain now. So we're starting from a formal, fully normalized one. How does this work? And this is actually the nice idea of this construction. So that's why I'm showing it in some detail here. So what are you going to do? Assume that you have such a production. Right, this one is not yet lexicalized. And it has too many non-terminals, 1, 2, 3 non-terminals, right? It has no single lexical item. So you have to do something about it. What are you going to do? Well, you're going to do the following. You're going to keep the left-hand side. You're going to introduce a new non-terminal, which records the old non-terminal, and in addition, guesses a lexical item called alpha here. So it stores in the non-terminal that it guessed an alpha. And then it adds a parameter, so this guy will have as many parameters or the same rank as this guy plus 1. And in this additional subtree, you'll put the lexical item that you guessed. So in this case, alpha. Otherwise, the rest remains the same. Now this production is lexicalized, right? Because there's an alpha here. It's a lexical item. Now you might have a problem. So now you have to, of course, write productions for this non-terminal, for this new non-terminal, right? I mean, you introduced it in the previous step. You have to write productions for it. So assume again that you have such a production. Now somehow you have to organize the transport of this lexical item. So here we now have this production for the left-hand side A alpha, where you guessed alpha. This, as you remember, has one additional subtree. So it has one more subtree. And if you want to simulate that right-hand side, you're going to preserve the information that you guessed, and you're going to preserve this x3 here. So you're just going to transport this alpha, which you already guessed in the previous step, and you're going to preserve it here. Now hands should go up and say, but this is not lexicalized. Right? There's still no lexical item in this production. Okay? So you have to deal with that too. So potentially you have to guess again. So if you have this problem, that you have now a production which looks like this and is still not lexicalized, you might have to do this guessing trick again. And why can you do it? Because you always have at least 2 non-terminals. Right? In each such production, you have to have 2 non-terminals. because all the others, the terminal productions and the monadic productions, they were lexicalized from the beginning. So I know that once I guessed once, I have at least another non-terminal left. I know that I have another one. So I can just take this one now and do the same guessing trick there. Okay? So this is now lexicalized. Now, finally, I have to stop this process somehow, of course. I have to somehow finish the whole thing. And this is where I'll need this funny doubly lexicalized notion. So assume that I have this kind of production, and I now have to build such construction or such productions for S with alpha, because I introduced S with something in the previous format or previous rules. So I will turn such a production, a terminal one, into these kind of productions, and I'll simply remove one of the lexical items. That's why I needed two, right? I'm going to remove one that fits with what I guessed. So if I guessed a beta here, I wouldn't be able to use this production, because I cannot cancel any beta here. No beta is produced. But for alpha, I can cancel the alpha, which will be here. I know this. I'll transport this guessed alpha all the way. And I remembered in this additional parameter, I'll always keep the alpha. And I'm going to simply remove it here with the sure knowledge that this x1 will just be an alpha. So it's just the same thing. That's the whole approach here. So what you can do is you can start from a context-free tree grammar, you can make it growing using somebody else's construction, you can fully normalize it, and then you can lexicalize it. And then you have a fully lexicalized context-free tree grammar for your starting context-free tree grammar. And mind that this includes all the tree adjoining grammars. Okay, so this is the result. So if you have this input context-free tree grammar, you'll get a lot of rules. Admittedly, you'll get quite a number of rules, but they're very systematic, right? They all follow this recipe which I gave you 5 minutes ago. So you have the original productions here. Here you have this one where you guessed an alpha and you cancel this here. There should be a similar one, yes, here, where you can guess an alpha or a beta and you can cancel this on the second side. Here, this is this one here, extended, or this one, yeah, so the delta can be alpha or beta. And the A productions, you see, they look very similar from what you started out with. So they don't look, if you remember the construction from Greibach normal form, this is achieving the same thing on the tree level, but it doesn't mess up the recursive structure as badly as transformation into Greibach normal form does. So it's very conservative, actually. Okay, now you could actually look at context-free grammars, tree grammars with non-terminals whose rank is always smaller than k. So the rank is simply, right, this would have rank 1 because it has one successor, and this is rank 2 because it has 2 successors. And as Engelfried, so Joost has already proven, together with some other authors in the 80s, as I told you, these context-free tree grammars have been independently developed in the theoretical computer science community, that this is an infinite hierarchy of string languages even, so not just on the tree level, on the string level, just the same. And you could now try to summarize the whole picture by basically trying to present a Hussar diagram. So you know that this is a Hussar diagram. And if you look very closely, this one here, context-free tree grammars of rank 0, this means non-terminal is never allowed to have any subtrees. Then this is the same as a regular tree grammar. This is exactly the same. Now this level here, this includes the tree adjoining grammars. It's stronger, slightly stronger than tree adjoining grammars because it has state behavior, which tree adjoining grammars don't have. And then you get the second level and so on. And this is all strict, as proven by Engelfried. And what you can show is if you go through the constructions very carefully, you'll see that the next level can always strongly lexicalize the previous one. So the regular tree grammars can be lexicalized by tag or by context-free tree grammars of rank 1. Then this can be lexicalized by level 2 and so on. So you can always go up one level and you can get lexicalization. If you don't make the levels, then of course context-free tree grammars can lexicalize themselves if you don't have any restriction on the rank. And for the linguists, the nice result is that context-free tree grammars of level 2 can strongly lexicalize tags. This somehow repaired this failed result. But something we don't know is whether this rank increase is really necessary. We don't know. It could actually be. So we know that this is necessary here. You cannot lexicalize regular tree grammars by themselves. This simply doesn't work. But from here on out, we don't know whether that's necessary to go up one level. We simply don't know. Okay, and here's some references, and in the second part it will be a bit lighter as usual, and we'll talk about machine translation. So thank you very much. Okay, so we'll all, I hope, enjoy the excursion, and the weather is somewhat better than yesterday at least. So now it's going to be the lighter part for today, right? So those who want to just enjoy a bit of fun, having a bit of fun on my terms basically, are going to have that, and you'll see some translations and you'll see some Russian again. So let's go. So here we are now in this second part, which concerns itself with machine translation, and this is actually where I'm at home, right? We don't do parsing competitions. We use parsers, as you will see towards the end of this talk, but we don't actively develop any parsers. But we do develop machine translation software. So I'll show you the basics, and you'll see again this is highly sophisticated machinery that is used there. In quotes, of course, but this actually gives you the best results again. Okay, let's start with the foundations. So a statistical machine translation system is simply, at least for us, a fully automatic computer system that translates based on statistical models and which are learned from parallel corpora. Now I have to, of course, specify what those terms mean. So if you actually want to do that, you have to get certain resources, and these are the parallel corpora. What's a parallel corpus? That's a linguistic resource in which you'll have text in one language and text in the other language. And in a particular way, namely that's such that you have a sentence-to-sentence alignment. Just in case you end up talking to your local linguist next week, maybe the week after, because you should enjoy DLT next week. A parallel corpus is the same as a sentence aligned by text. Yeah? He might call it like that. That's the same. But it's not the same as a comparable corpus. A comparable corpus just has two texts which speak about the same thing. But it doesn't have to be a translation of each other. Okay, what's a sentence alignment? Well, that's simply an injective partial mapping that assigns sentence numbers in one corpus or in one language to sentence numbers of the other language. So overall, a parallel corpus, for those who like mathematics, is nothing else than three partial mappings. One, sentence numbers to sentences in the source language, a sentence alignment, which links the two sentences together, sentence numbers, and a second mapping from the natural numbers to strings, which tells you the target sentences, assigns to each sentence number a target sentence. Of course, these will typically have finite support, right? So it will just stop at some point. It will be partial from then on, because you don't have infinitely many sentences. Okay, here's a simple example. This will be German. I don't know how much you can get from that, but this is actually a reasonable example. So it reads, we can help countries catch up, but not by putting their neighbors on hold. And the German is, well, a good translation. It's actually a reference translation of this. Here's a questionable example for the same. This again, German, however, but the translation actually is the It's a reference translation. So this has actually been said. When this was said in English, the human translator actually said this, but in this case it's actually the inversion. So it's the negation of what the other guy said. Well, no, that just happens. You have to deal with that. Here's the English-Russian example, and you get to say what it says, because I have no idea whether this is a good translation or not. Indeed, Republican lawyers identified only 300 cases of electoral fraud in the United States in a decade. I don't know how to read this other stuff. And is that a good translation of this sentence? It's okay? Okay. So that's also a reference translation. And in that case, it seems to be a good one. So this is the kind of information that you'll find. So once you actually align the sentences, so you take two sentences which are translations of each other, you'll have pairs of such sentences. So this is the corpus that you start with. Now what is a sentence? Well, it doesn't make sense for us to speak about individual characters usually. So for us, a sentence is a sequence of tokens. So words typically. Well, formally the result of tokenization, whatever that is. Normally, so that's the word. So when I say the third entry in a sentence, I mean the third word, not the third character. There are some exceptions. If you deal with Japanese, Chinese, or similar languages which are more pictorial, you don't have a notion like word. So then you have to deal with characters. So here, if you have this sentence, we must bear in mind the community as a whole. I'm pretty sure you cannot stand this sentence anymore. Then you have length 10, because you have just 10 words in it. And if you had a full stop, it would count as one word too. Okay, then there's just some notation. So given the sentence, you of course have positions in it. That's just the same as your usual positions in a string, but on the word level here to say. So if you want to have the ith entry, that's the ith token, so the ith word. You have the inverse, so all the positions at which a certain word occurs, and you have a range from I to j, that's called the span, and this is the sub-sequence, sub-sentence that starts at the ith word and runs all the way to the jth word included. So this is just an example, but I think this is so easy that I can just go over this quickly. And then you have a word alignment, and this is one of the magic parts which I'm not going to tell you how you get this. Okay, so there is an automatic process which gives you, given such a resource, such a parallel corpus, will give you a word alignment. And a word alignment for two sentences is a relation between the positions. Right? And this is typically graphically represented like this. And if you work in the area, then you'll see this actually. So this in a file, it will generate this, right? This is just a format for presenting the pairs in the relation. Now in this example here, this is English-German again. This is actually a very bad alignment. So all it did is this we to wir, that's okay. Must to müssen is okay. But bear in mind the community as a whole has been aligned to this word here completely. I know that German is very expressive, but this word doesn't express all of this. So yeah, and then there's some additional spurious alignments. So this alles actually means whole, so that's actually kind of good, but this one not so. And here actually this is kind of important because it says we should not do this, what it says behind, that's why the semantics actually is inverted. Right? If we try to vergemeinschaften everything, then it would indeed say the same as here, but yeah. Anyway, here's that's actually a nicer alignment, so this is how an alignment should look like, and sometimes it does. It's not perfect, so for those who know a bit of German, you maybe know that putting has little to do with wir, which means we. Yeah, this is somewhere here, right? This would be the better relation. But you know, it gets things wrong. It's an automatic process. And this is one of the processes which is let's say, mathematically at least a bit challenging, right? It's not super complicated. Given 2 more lectures, I could also tell you how this works, but it needs quite a number of models. Here's actually a Russian example. And I can just read it, but that wouldn't make a lot of sense for me. So you get to say again whether this makes any sense or not. But this is what I have to work with, right? If I train, and that's what we did, a student of mine at least did, she took the Yandex corpus. It's about 1 million sentences in Russian and in English. These are 2. This is 1 pair in that corpus. And we produced the alignments for it, and that's what you get. Is that sensible? It seems...
Correct.
The translation is already incorrect.
Yes.
Okay.
It also depends on the previous, on the context.
Ah, okay.
But it copies some words which in English are expressed with the pronouns, and it copies some words.
So this them here, or?
Yes, with them it's a noun is copied probably from the previous sentence.
But that's, of course, for us, that's very bad because we will work on a sentence level. We won't have access on the previous sentence. So for us, this is all the information we'll use. So we will have, as you will see in just a few minutes, we will have rules that will tell us, okay, you can reasonably translate the English them as na cassette or something. Which probably means cassette or tape or something.
Yeah,
okay. And demo means down, or? Okay. 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 So, but this is what you have to work with, right? This is the data that you get. It might be good in some cases, it might be not so good in others. Okay. So what we typically work with is the Europa Corpus, because we work mostly on German English. Makes some kind of sense, right? At least all of us in my group understand these 2 languages. Some others do understand a few more, but all of us do understand German and English. And so that you get an idea for the size or for the scope, it has about 2 million parallel sentences, so 2 million sentence pairs. About 50 million words in both English and German. If you're actually wondering, and you always thought, but the English text is always shorter than the German one, here you see that actually German uses fewer words, but we tend to we really like our long words, right? We really like to put several nouns into one, and we really like this, creating long words. So this will count as 1 word, of course. That's why we have 3 million fewer words to express the same thing. The text is actually longer in German, unfortunately. So this corpus is already sentence aligned. So the first sentence in German will be the first translation of the first sentence in English, and so on. And it's automatically been obtained from Parliament proceedings. This means you should use this corpus with some care, right? So if you want to use this in a standard, say, university setting, it might happen that in your translations people address themselves by Mr. President or something, because that's a very common opening in Parliament. Yeah? If somebody comes to the Parliament, he typically says, Mr. President, may I bring the following to your attention, or something like that. And it will realize this is not expressed in all languages. The English guy, translator, maybe said, oh yeah, this is just a phrase that is said every time, he might just drop it. And then our translation system learns, oh yeah, this Mr. President you can introduce all the time. It doesn't correspond to anything on the English side. It's like your and at the beginning of the sentence, right? You wouldn't translate that into German, because in German you wouldn't start a sentence with and. That would sound weird. But the system will learn such things. So you should be careful, but if you use this in Parliament type settings, then it's actually quite okay. If you want to do a bit more, and I have one Chinese PhD student working on English-Chinese, unfortunately he can't read that. So his output, I have to trust that it's good. It's just a bunch of funny characters to me. So he has about 10 million parallel sentences, quite a few more words. There's no such thing as a word in Chinese, so I didn't know how to count this actually. You can actually, the concept exists, but it's disputed what actually constitutes a word and what not, so I didn't give you the number. it's a lot more characters. So it's more than 1 billion characters. It's also sentence aligned but not word aligned, so this you have to do automatically again with the usual results. And this is even worse because this is from official UN documents. It's larger, but this is even more formal in terms of speech. So this one, if you want to use it in everyday language, it will not work at all because the terms that they use are really weird. So these are the official documents that the countries make between themselves. Yes?
So that's because of this officiality that you have so long sentences.
Yes, yes.
Because in real life you don't have average length of 25 words per sentence.
Yes, that's certainly true, and you get a lot of itemizations, for example, which will create sentences that are more than 200 words long, which you in speech couldn't process. Yes, such a list I actually haven't seen yet, but there's lots of items what they actually agreed upon. So often you have something like an introductory who was there and who was not there, who was unfortunately missing, or unfavorably absent, as is typically expressed. And then there's a lot of items. We agreed on the following things, and then dum, 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 dum. Yeah, well, it doesn't happen that often in normal language, right, that we speak in itemized terms. I want to tell you the following things. 1, 2, 3, 4, 5. If you speak like this, this is perfect translation software for you. And as I said, we tried a small experiment. I don't want to keep the, there are other people at my institute. If we do a lot of experiments with big data, the computers are busy, right? So we did a small experiment on the Yandex corpus, which only has about 1 million parallel sentences, and it's Russian English. So again, I can only understand one side, and the others is again consists of funny characters. What is the basic model that you'll use? So the dominant model nowadays are so-called phrase-based models. And you'll see this is really highly sophisticated technology. It's been introduced only in 2004, so the whole area is really young. And the phrase here is the basic translation unit. A phrase is simply a sequence of words. It's the dominant model for many language pairs, including Russian and English. So if you want to know what Yandex uses to do translation, it's a phrase-based model. But don't tell them I told you. Google does the same. Also for Russian English, uses a phrase-based model. There are few exceptions. If you know Chinese and you use Google for Chinese to English, it will not use a phrase-based model. But for most languages that you can use in Google, it will use a phrase-based model. And by the way, Google will always translate via English. So if you want to get something translated, say from Russian to German, please don't, right? Translate to English. It will be much better because what Google will end up doing is it will translate your Russian to English and then this English to German, which will basically double the number of mistakes it can do. And once you have a gobbled up sentence, so once the input is not proper anymore, the result gets much, much worse. Because that's a kind of assumption that we make, right? We want to be sure that what we get as input is already grammatical. We don't check this. Okay. So a phrase is simply nothing else than a contiguous sentence of words. So it's a span in your original sentence. So the main definition, and actually the only one for phrase-based models, is when can you extract a phrase pair? And a phrase pair is just 2 spans. That's called consistently aligned. If all the indices in the one span, from I to J, I prime, and if for all indices in this one span, J to J prime, so this is just an alignment. So here you have an L that is in this indice, in this span here, so between J and J prime, and you have a link that goes to this particular L that you selected, then also the other side must be in the corresponding span on the other side, right? So given on the picture, if you select this span here, im Zusammenhang mit, from 9 to 11, then you have to take, for example, this 9, because there's a link here that links to this 9. If you were to take 9 to 11 and 8 to 9, this would not work, because here you can select this 8. This has a link to this 8 here, which is outside of the span on the upper side. So it's a very simple definition, right? You just have to look at the selected intervals, this one and this one, then you look at all the links that originate or end up there, and they have to, the other side has to be in this particular interval that you selected as well. And the main procedure simply asks you to extract all the consistently aligned phrase pairs. That's it, that's what they do. There will typically be a length restriction to make it feasible, but in principle that's all they do. So here, for example, for this 2 sentences, you would extract könnten should translate as would like. So this is the minimal one that you can take. I'll only do minimal ones now. Sie can translate into your. This can translate into I. This actually translates like this, like this, like this, like this, like this, like this. And this is somehow, this is often the case in English and German. Somehow this verb here that was so far away that, yeah, that has no partner. That happens in the alignment. Okay, so this is what you would get. So formally you would get this. This corresponds to the following rule, so you could translate eine Auskunft to advice. Now you could also, so these were, as I said, only the minimal phrase pairs, only the smallest ones, making them as small as possible. You can also extract combinations of those. Right? You can put 2 of them together if they're neighbors. So 1 and 1, neighboring is 2 and 2, and 2 and 3, and neighboring is 4 and 4. You can put them together, and it will give you another consistently aligned phrase pair. It's going from 1 to 2 and to 2 to 4. And if you have such an unaligned word here, like geben, you can add this here. You can extend this from 12 to 13 to go from 12 to 14. Since there's no alignment, it doesn't harm anything. So you get also additional translation pairs like könnten Sie, would like your, and things like that. Okay.
What about punctuation?
Punctuation. Punctuation, there's no comma here. Wait, maybe I have a comma in the next example. Yes, there's a comma in this example. So I cannot delay you for 2 minutes.
Okay.
Good. So here's just another way to represent this. If you're more the graphical type, you can use the alignment. You can represent this relation as a matrix, right? So this is just the alignment represented as a matrix. And if you want to get consistently aligned phrase pairs, you have to find rectangles in this matrix. So this one, for example, would work. This one would work because now in this lines on columns there are no additional alignment points. This one would not be okay because on the second row you'll have an alignment point which is outside of the marked rectangle. Okay, so here's the example for Russian, and you'll see some punctuation, a comma here, which was probably really clever rules. As you said, it's not quite perfect, this alignment, but this is what you would learn from this. This was what the system would learn here. The system would learn I can translate I was into ja, will or something. And down and copied them could be translated into this long expression here. And the one who said is this kind of thing. That's what the system would learn. Right? And you would hope that in a large corpus, such a bad situation would occur only infrequently, right? So that you don't get too many of those bad rules, or at least you don't see them very often. Okay, so this is all that happens inside Google. They extract rules like this. They do this, of course, for terabytes of data, right? And they count how often a rule was extracted. This is the weight of the rule, so such a rule maybe which is not so good. I don't know whether it's good. Is this good? Is this helpful? No? Okay. So you would hope that you would extract such a rule only once or twice or 3 times, and then it has such a low weight that it's not going to be used actually. Okay, so one important thing, you're not linguists, so you probably don't make that mistake, but phrases have nothing to do with those constituents, right, that we had yesterday. So the phrases are not necessarily linguistic phrases, not necessarily noun phrases or verb phrases or anything like that. Phrases for computer scientists are simply contiguous words or tokens. So in German, this would be a non-linguistic phrase pair, because this article should belong to the next noun, not to the previous one. Okay, actually, of course, the linguist said, but you should never do this. You should always only translate linguistic phrases, right? Because that makes more sense linguistically. Problem is, if you do it, your translation system sucks even more. So people don't do it. But it has been tried. And there is actually a famous saying by IBM folks who pioneered this approach or the previous approach. And the saying, it's not quite clear to whom to credit it, but the saying was, every time I fire a linguist, translation quality goes up. So of course they started this process with a lot of linguists, thinking that translation should actually have something to do with the meaning of the sentence. Turns out it has not. So you can do this, you can build the best translation system without having any idea about Chinese or whatever languages you actually translate. So you don't need any linguistic knowledge. None. So it's not, I don't know of a single publication which shows that having some linguistic tool actually helps. And you'll see more of this unfortunate state of affairs later on. So this has actually been improved a bit. So I told you that Google always uses phrase-based models, but for Chinese to English it uses something else. And these are hierarchical phrase-based models. And here you see a hierarchical phrase-based model. I'll start with the motivation. So this is a simple German to English again. It's the alignment is handmade, so I did the alignment. So you see what German expresses. So here you have a problem. Now try to find a consistently aligned phrase pair that involves the German hat or the English board. Can you find one? Can you find a consistently aligned phrase pair that contains board? Yeah, you would have to take all of this, right? Because you're not allowed to split and take only hat and gekauft. But you're not allowed to do that. You have to take a phrase is a contiguous sequence of tokens. So if you want to extract a phrase pair for hat or board or gekauft, you would have to take here, because of the board, you would have to take gekauft. Since you have to take a phrase, you have to take all this, what is in between. Once you take all what is in between, you have new alignments and you have to take all the rest in the English as well. So the only consistently aligned phrase pair, except from the two sentences themselves, right? This you could also extract, would be this one. But this is, of course, not very useful, right? I mean, it's very useful if you get exactly this query. It's very useful then. But if you get any sentence that contains board, and it doesn't have cars or fuel-efficient cars, you're screwed, because it won't match. So you didn't actually learn anything about board, right? You didn't learn how to translate board. And for some languages, in particular also German, this is a problem. This thing that the verb appears at the end and is realized as some kind of auxiliary in the verbal position, so in the second position. This happens very frequently in German, for example, that a simple verb in past is realized as an auxiliary and the main verb at the end as a participle. So that's a problem, and that was of course identified. So here, that's what I just said. You would have only one rule, which is very limited in its usage. So here you have the problem that the restriction to phrases yields undesirably long phrase pairs. So then in 2007, there was a guy from the university, from the ISI, the Information Sciences Institute at the University of Southern California, David Chung, and he said, well, let's have hierarchical phrases, where you can have phrases inside phrases. Okay. So you now have phrases with gaps, and the gaps are noted with variables, in this case an x, but you can take y if you like y better. And then you could try to extract something like hat x gekauft, board x. Okay? And if you have something like this, or you have this phrase pair, then you can plug this for the x and you get the sentence back. right? So you can plug this, for example, into this, and then you can plug into this X, you could plug something else. You could actually plug this into this one. Well, we'll get a messed up sentence, of course, but so there's no restriction. You can plug everything for everything, right? If you have two rules, you can plug them any way you want. There's only one variable. Everything goes into everything. There are two restrictions. Rules in which you have just the left-hand side consisting of a variable are not allowed. This has obvious problems in translation, right? Because you could always use this rule. It's not so nice. Typically, you have a restriction to at most 5 gaps. Since this is difficult to display, and actually in most cases they actually limit themselves to 2 gaps. So a rule like this would also be illegal because it has 3 X's. And you also, again, for parsing efficiency, you're going not to allow 2 adjacent X's, because then you could play with how far this X should actually go in the source. So there should be a lexical item in between those X's. Okay, so how do you get the rules for this? Well, you do the thing as usual. So you do what you do anyway. You extract phrase pairs, consistently aligned phrase pairs, just like before. And now what you do is you try to find a phrase pair that contains another phrase pair. Like here. This phrase pair is contained here. Ein neues sparsames Auto, a new fuel-efficient car. And if you have such a situation, you can create a variant of the first one where you subtract, so to say, the phrase pair that you found. So you're going to get a rule like this. You have to check that it fulfills the restrictions I just mentioned. So it should not remove everything from the left-hand side, shouldn't create X's that are adjacent to each other, and so on. But this is how you would obtain this rule. Okay, this is how you get all the rules if you want to translate Chinese to English. It's a highly sophisticated process that utilizes the linguistic knowledge to the best effect, at least right now. And you iterate this. So once you did this, you can actually use this to do the same process again. In this case, it won't be successful because you cannot get this. This away will generate adjacent X's, and this will also generate adjacent X's. But in principle, you could do it. Now, we still have a bit of time, so I'll try to show you how these things actually perform. And of course, before I can tell you how they perform, I have to show you how this is evaluated. And you know, we're cheap. We don't evaluate by humans, because that would be way too expensive and take way too much time, right? A test set typically has about 2,000 sentences. Getting 2,000 sentences evaluated and scored by a human will take more than a week, right? So what you do is you do something, small changes in your translation software, and then wait a week before you see whether this was nonsense or not. Not a good idea, right? It's not exactly rapid development. And you have to pay that guy actually to do this work. Okay, we are at the university level. You can get a lot of slaves, so to say, by doing master projects or seminars or something like this. Yeah, you can get them to do a few translations. But 2,000? So I wasn't really doing that so far. So the most we actually ask students to do is about 100, scoring 100 translations. So then you need 20 students already, and yeah. So you see, it's infeasible to have human annotation. But let's have some fun with the translations first. You probably already read the input. It probably makes sense to you. It should. It seems to be a good sentence. I omit the punctuation usually because it adds no value, basically. Hierarchical phrase-based model that we trained. Remember, it's a really small model. Yeah, it's a small model that was trained fast in a couple of days, and based on the Yandex corpus, which they released, so everybody can use it. Our translation is Republican strategy, resistance, renewal, elect Obama. You get the idea, but it's not very good, right? If you use some competitors, this is Google Translate, the Republican strategy of resistance to the re-election of Obama. This is certainly better. Yandex, I don't actually know whether they have the same base technology. They use the same models. And also the interface looks surprisingly similar. But Republican strategy of resistance for the election of Obama. That's the only difference. So you probably would guess that they've been trained on very similar resources. Maybe they used actually almost the same. Here's a bit more complicated one, at least it's longer. That's all I can evaluate. Our translation, in addition, these laws reduce period early voting. We didn't know this word. We had no idea what this is. In such a case, you're just going to copy it. If you're translating from Russian, you're screwed, right? Because then you have all these funny characters in your output. It actually works reasonably well for other languages, right? Because you'll not see, I don't know, George Washington. Well, depends on the text that you had as training data. But you will not see all names, all geographic locations in the training. But often you can actually copy it and get around this issue. So the Ural mountain you could just translate as Ural. Problem, of course, with languages which are written in funny characters is that, well, you end up with funny characters in the output. So of course, Google will not do it. Google will also do this, right? They will also do something like this, copying the input to the output, but they will have a component which renders this in English letters. So they will phonetically render this in English letters just to get the names and the geographic locations and stuff like this correctly. But I don't have the resources to have somebody try to write a phonetical system now that translates into English. So our corpus never contained this particular word, and this will just be copied. It's probably in a very bad position either. But anyway, voting, this word, right, registering voters in the day of voting, and take the citizens have the right to vote, have a criminal record. Fantastic. I didn't understand what was going on. So, yeah. But that's what you can get from 1 million sentence pairs. Google Translate, in addition, these laws reduced the early voting period, abolished the right in voter registration on the day of expression. I don't know what they express, but and the right to take away votes from citizens who have a criminal record. The last part is very well expressed, so this I totally understand, the last part here. And the right to take away votes from citizens, the vote, but yeah, from citizens who have a criminal record. Yandex, yeah, it's very similar, so they seem to be trained on the same data. In addition, these laws reduce the early voting period. Somehow there's a punctuation or something missing here. This is not a good continuation. Will void the law of registration of the voter on the day of will. Well, I don't know, it's also not too great. And take away the right to vote of citizens with criminal records. Google was a bit better here. Realizing this as a relative clause is a bit better than as a prepositional. Anyway, so this is what you will get. And you see, of course, that if you use such a small system, you will not be as good as Google Translate or Yandex. How do you evaluate? It's a fantastic methodology that is used here, developed in 2002. So again, relatively recent, only 12 years ago. What you need is, you need translation output, and you need a reference. So you already know what the translation is, but you're testing your system on a set of tasks where you know what the reference should be, and you're evaluating in this way. By the way, it's called bleu or whatever you want to pronounce it. Bilingual evaluation understudy. So the IBM folks tend to have strange titles. So what they do is they compare the translation output to the reference translation. Actually, not they, it's what everybody does nowadays. And you're going to count n-gram matches up to a certain n. And you're going to normalize the count by all possible n-gram matches. If this sounds familiar, it of course is the same as something like maximum likelihood, but yeah. So the precision for I is the number of matches for n grams of length I, or I grams in this case. So it had nothing to do with Apple, by the way. It's just a number here. So between T and R, and you divide by the number of all potential matches in the translation. So that is, well, 1. So that's the length of T minus I and plus 1. And then the blue score of rank n is this formula. This is the geometric means of all the precisions of level I running from 1 to n. And then there's this factor, which is the Brevity penalty, and this is again a highly complex mathematical expression, which just makes sure that your translation shouldn't be too short. right? So this just says it's the minimum between 1 and this fraction, and this fraction is just a fraction of the length of the translation by the reference. So you get a slight penalty if your translation is shorter than the reference. Because this was a usual trick how to get this score high up, right? Because if you're very short, there are very few n-gram matches which are possible, and even if you get very few, you'll have a high score. Okay, so here's how you could score this. So this is all English now, so everybody is free to participate. The rotated with miniature cameras mounted on helmets recordings are checked at the airbase in Kandahar and then sent to London, where they are on the internet. So this is actually typical data that you get from the American research agencies. The reference is the images taken with miniature cameras attached to troop helmets are monitored by a command center in Kandahar and then transferred to London, from where they are uploaded onto the internet. So this is what you should have produced. It's not quite what Google Translate in this case produced. Now you're basically going to check, and I'll go over this very quickly. You're going to count how many things you got right. So you got the there right is there. The location is irrelevant, right? You're just looking for the. Rotated doesn't exist. Width is there. Great. Miniature is there. Cameras is there. Mounted? No. Translate as attached. Good translation, but you're screwed nevertheless. It's not the same word. On, for some reason on doesn't occur in the second test. In the reference, so no credit. Helmets, they're there. Lucky you. Recordings, not present. R is there, checked is not there, and so on. So you run down, you're counting the 1 grams all the way till the final dot, which you almost always get. So you have 20 of 29, 1 grams. Now you're going to do the same thing with 2 grams, which are just phrases of length 2. So here with miniature, okay, it's there. Miniature cameras, it's there. In Kandahar, it's there. All the stuff in between is not. Kandahar end, it's there. And then also there, to London is there. Where they is there, they are, and the internet. And the internet and the dot is also there. Okay, so you get 10 out of 28. 3 grams. Miniature cameras. In Kandahar end. And Kandahar and then the where they are and internet dot. So you get 5, and this is the only 4 gram, I believe. Yeah. So then you can use the formula, and you get a score. In this case, the score is 17.46%. Sounds bad. The translation is not so bad, but you still only score 17. Okay. So this is how you score. This is really the scoring procedure, right? Nothing else happens. This is the score. This is the target function. Now it is known that blue should be used with multiple references. It's known, but not done, because often you don't have multiple references, which require several translators or the same translator to produce several translations. They get annoyed anyway if they have to produce translations for machine translation, because they think machine translation is going to make them going to replace them in the near future, so they're not very happy to produce translations for us. So getting them to perform one translation, what's actually their job, is typically doable if you pay them right. Getting them to get several translations is next to impossible, because they don't want to be very cooperative. Should be used for documents, not just sentences. Yes, but actually this is kind of done. Primary evaluation for MT systems, that's certainly accurate. So if you can build a system which beats the best system in terms of blue, you're going to be published, no matter what. It doesn't matter how sensible the system is. If it performs better than other systems in terms of blue, you will be published. And why is this accepted as a scoring tool? Because it correlates reasonably well with human judgments. So here you see the blue dots and the red dots. These are human judgments. And here you see the blue score. As a variant of the blue score is annotated here. So along this line you would have perfect correlation, and you see that this is reasonably close, so to say. So sentences which have been marked bad by the human evaluators are also having a bad blue score. Okay, so here you see some systems. This is Russian to English, actually. I had some fun with that. So what we did, we trained a few systems, and I said it's vanilla. Why do I say vanilla? Well, because we didn't do anything, right? We just used the corpus, started the system. We didn't do any pre-processing, post-processing whatsoever. So we just trained the system. What you get is a blue score of around 20. You'll see this tomorrow, what this guy does. It's a bit better. And if you use hierarchical phrase-based, you get actually quite a bit better. We didn't do phrase-based, but I would assume it's quite a bit better as well. The best system last year for this particular language, so Russian to English, was a system out of Cambridge, I believe. And it had a blue score of 26 almost. But there you would actually have to invest quite a bit of additional stuff. So what you see here, I just noted, so what they did is pre-processing. So before doing the translation on the Russian part, they did Stanford Core NLP. This is probably to normalize things. Morphessor, this is annotation for morphology. They stamped and post-tagged. And in the post-processing, though that's on the English, they're going to use a 5-gram language model to rescore and some other stuff. So yeah, they did a lot of additional stuff, so to say, to improve the score beyond that, what you get from a vanilla system. Okay. And I want to show you in the last 5 minutes, I'm going to show you how syntax-based models work. And this is a model which uses linguistic information. But the problem is, it typically doesn't help. So there, in this case, that's what we do. However, most of the time, you would have the following chain. You would have an input. You would run the input through a parser, and you would translate the parse trees to get the output. So what you start off with would then look like this, right? You would have parses now for the sentences. Actually, parses for German look kind of funny, but you know, it's a highly inflected language, so you have all sorts of annotations. That this is a dative, for example. Yeah, so. And if you, just to be on the safe side, so this you won't understand, I hope at least. So this is now Arabic. So this is English Arabic. So actually it's written from here to here, right? So this actually, I realized yesterday, it seems that Arabic and Russian at least have the same phenomenon that you can put an and. You can put this guy here, this expresses and, at the beginning of the sentence without any semantics. So this is this wa here. Transliteration just means it's a romanization of this funny looking things here. So we typically work on this because this just creates all sorts of problems with the encoding. So this is what you have, right? So this is now transliterated. This has already been turned around. So the wa is at the beginning. You cannot read it a bit right here. This is Serbia, right? And this is all Yugoslavi, something like this. So you might guess that this has something to do with Yugoslav. But yeah, that's really all you can. And this is Voislav, if you can't read it, right? So this is phonetically expressed in the Arabic. Okay, and what we do, and this is really the last thing I'm going to show you, is how you get rules for a syntax-based system. Well, you now have those two sentences, the alignment. The red doesn't mark anything special, right? It's just so that you can read it easier. And you have the parse trees for both languages. And what you'll do is you'll use the same principle of this consistent alignment on trees now. So say you want to select this node here, Yugoslav, then you know by the consistent alignment principle you have to take this on the other side. And then these two are actually already consistently aligned, right? Because in its subtrees there's no more alignments. So you could extract those as a rule. You could say, okay, I can translate Yugoslav into this al Yugoslavi. Al, by the way, is just a determiner in Arabic, something like the. And then you just leave a state here. And why this state is named QY, it doesn't matter to so much. But you're going to repeat that, and you can extract president and Voislav and so on. And at some point you want to extract maybe the signed, or maybe let's do this one first. Then you look at this part. So states you cannot extract by themselves. So you have to take at least some part of the parse tree. So if you want to extract this, in this subtree you have an alignment to here and to here. So you have to cover both these two states here, and you have to go at least to this NP, and then you have a consistently alignment again. You can extract this as a rule. NML, QY, QP, and so on. There it's gone. Now let's try to extract the signed. So I just made it a bit bigger. Nothing changed really. So I want to extract the signed. The signed unfortunately has alignments here and here. So since they are not in, they're only in this subtree or even larger, I try to be conservative. I have to extract all this, including these alignments here. So I have to take, well, I can take this for free, right? It has no alignments. And so I have to take the whole sentence on the other side and can extract the sentence, a rule from that, which will look like, actually I haven't written down this rule. It will be a very big rule with S on this as the left-hand side and this as the right-hand side. Okay, so these are the rules, and with that you can then rebuild the trees and perform the translation. And these will actually give you the rules of what is called an extended top-down tree transducer, and you'll learn tomorrow in the first part, where it's about the theory again, how this device works, what its theoretical properties are, and so on. Just a teaser that this is already such a device. And these are simple. Again, you might disagree, but for us they're very simple. They're relatively easy to train, only recently, however, been done. And they're symmetric, which is also good. And you can actually use them if you want. But they also have a bunch of disadvantages, but I'll get back to this tomorrow. And I'll also show you an evaluation of those in the very last talk. So tomorrow in the not so hard session. Thank you very much.